All right, so hopefully people are able to join on Zoom. Just a reminder that the video is due tomorrow night. So make sure that you're working on it, finishing up, and also be working on your project. Your first progress report is due next Friday, I believe. So meet up with your group, meet regularly, and yeah. All right, so let's we're gonna keep working on the packet as much as we can today. So last time we looked at the wedding seating arrangements, and we decided that this models what we call a bipartite graph, which is this two-part graph where inside these two sets of vertices, there's no edges, but there can be edges inside or between the two sets. That's perfectly fine. That's a bipartite graph. So our solution for the seating chart is to say if there are if there's a 3 cycle, so 3 people who dislike each other, then there's no solution. And so the solution is to go through and traverse the edges in our graph and label each person. So like label the first person table 1, the next person table 2, and so on, alternating labels as we go. And if we get back around to the first person and we've done that, then great, we found our solution. But if it's not possible, so we end up to a point where one person sits and another person, if they both have to be table 1 or they both have to be table 2, then there's no solution possible. And that's an odd cycle. So an odd cycle in our graph could look like this, which is a 3 cycle, or 1, 2, 3, 4, 5 is also an odd cycle. And so any configuration of odd cycle that we find, if that's present in our guest list and the list of animosities, then there's no solution possible. The next one was the movies, where we said there's a set of movies and we want to show one movie on Saturday night, one movie on Sunday night. And we can show multiple movies at the same time. So the first thought is to maybe draw edges. So each customer picks 2 movies and so on. And we want to find which movies, like, let's schedule one on Saturday, one on Sunday, and figure out if there is a solution possible. And it ends up that this is the exact same problem as the wedding planning, where instead of setting it up where the customer is has an edge to the movies, we ended up saying that the best solution has the set of movies as vertices. There's an edge between 2 movies if a customer wants to see both of those movies. And so then we do a similar algorithm where we go through the graph, either maybe BFS or DFS, and we label them. We label each of the movies, one Saturday and Sunday. And then the same idea of if there is a conflict, then there's no solution. But if we're able to get through all of them with no conflicts, then we've found a solution. So our issue with having vertices being customers in movies is it's not immediately clear if there's a conflict, why there is. And so it becomes clearer if we have option 2, where we say the vertex set is just the set of movies. So this becomes clear. So that's our best solution. All right. Any questions on those before we move on? Okay. I also just want to mention something that someone talked about or came up to me afterwards is if we have, like, let's say we have movie 1, 2, and 3. So this is a bipartite graph, that's fine. We've got movie 4 over here. If, as we're labeling things, if there's an edge between 3 and 4, then this ends up being not a bipartite graph. So once you add, if we have these two sets, once we add an edge within that set, then it becomes not bipartite. So either the graph is or it isn't. So just something to keep in mind as we go. All right. So our next question that we'll talk about is our job is to arrange n ill-behaved children in a straight line facing front. So like we're at the playground and it's time to gather all the kids after recess and they're all standing in a line and so on. And so there's n of them. We are also given a list of statements saying child I hates child J. So I hate J. So maybe, I don't know, Susie hates Jim, something like that. And once we have that information, we don't want to put, so let's say this is Susie and Jim. We don't want to put Susie behind Jim because then Susie could throw something at Jim, right? No violence in our playground. So we want to put Susie in front of Jim so that because they're all facing front, Susie can't turn around and throw something. So that's what we're given. We want an algorithm that tells us how do we order this line in, or says that it's not possible to do this in n plus m times. So typically n is the number of vertices, m is the number of edges. Seeing that we've been given that there are n ill-behaved children, that kind of tells you how we're going to structure the graph. So keep that in mind. So that's the first question. So let's work on that for a bit. So how do we order this line of children so that there's no violence involved? Any clarifying questions before we begin? Okay, go for it. I'm gonna try and figure out Zoom. All right, let's come back for a moment and just make sure that we're all talking about the same thing. So hopefully we've been staring at this for a minute. What's our vertices? The children? And what's our edges? Hatred? Okay, so if Susie hates Jim, how do we store that edge?
Peter first, and then T.
Okay, so this means that we store it like this, right? So yeah, so this is kind of what I had in mind. If as you go through the algorithm, you find that maybe you need it to go the other way, that's okay too. But this sort of structure where our graph is directed meaning there's an arrow here. So in an undirected graph, so like in the wedding table where if Susie and Jim are both invited, then if Susie dislikes Jim, Jim also dislikes Susie. That's not necessarily the case here. So the arrow, the direction matters here. Okay, so as you continue to think about this, I want to kind of guide your processes where let's say they're like all out on the playground. Maybe I can draw a stick figure. And so they're all out at the playground playing dodgeball, whatever. And we know these relationships. And so we are trying to call the children to line up after recess and put them in this line in an order. So the question is, how do we find that order if we know all these relationships? So how do we go from this kind of mishmash of children to an ordered line of children? That sound good? It's clear where we're going? All right, continue. Let's record this. Okay, let's come back and chat about it. I feel like maybe we may have reached the limit of what we can do by ourselves. So, so I've drawn this playground here of 5 children. And so we have a situation where D hates everybody. E hates A hates C, and D hates B. So the situation that we absolutely don't want is for the teacher to put D in the back, and then E, and then E hates A hates C. Yeah. So like this is the worst case scenario, right? Because then there's rocks all around. So very not good. How do we fix this? So one option is which is to start with C. And why would we start with C? Yeah. 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 Let's say good terms. I don't know. C's on good terms with everybody. Like doesn't hate anybody. So and this is a good start. The way that can I please? Oh no, disappeared. Where did you go? All right, we're gonna put it down here. No. Okay. So if we decide in this example to start with C, what are we doing in general? Like, so we're starting with C because they're on good terms with everybody. So we're choosing, yeah. Probably. I mean, this is a decision that you can make. Yeah, because maybe we don't want any forward, probably in this scenario, we don't want any forward edges. We only want edges going backwards. So we start with kids that hate no one. Maybe put them in the back. So then we've got, so we put C in the back. And then what do we do? Yeah, sure. Hmm. Okay. A, D. And so you said, um, D hates a lot of people, so don't choose them yet. In graph theory, we have a term for this. The number of edges associated with a vertex is called the degree. And so, um, how many edges that vertex has? Specifically for directed graphs, the in degree um, is, so let's actually draw that. So the in degree is that one. The out degree is the number of edges that are leaving that vertex. In degree, number of edges coming in, out degree, number of edges going out. So, so maybe prioritize lower, prioritize vertices with lower out degree. Okay. So we can do that. So A and D. So now what do we do if we are not going with D? What do we do with A? Do we put them in line now? All right. Now what do we do? Repeat. So we look at who hates A, which is E and D. E has a lower out degree, so maybe we choose E. And then we look at who hates E, and then we get just D. And so by our rule, we put D here, and then what? Yeah, that's correct. Yeah, so we're kind of doing this like backtracking, which depending on how we structure the graph could, so maybe this is the sort of situation where we want to just like flip all the edges. Just to allow us to like go backwards, because normally we don't allow going from C to A. We would only go from A to C. So we're kind of maybe playing fast and loose with the rules here. But yeah, so the idea is that C does not like, no, A doesn't like C. C is ambivalent to A. Okay, so we're almost done with our line where we've got, so D hates all these people. And then we've got B left. But if we put B here, then, oopsie. Then we got start. How do we fix this? Idea? Yeah.
Then deal.
Send B all the way to the back. Okay. Um, So how do we keep track of that in our algorithm? So we started with vertices that didn't have any in edges. And we chose, actually what we did, we started with a vertex that didn't have any in edges. So we started with B, or with C. How do we make sure B stays safe? Idea?
All the vertices that have an algorithm row, then find vertex that has algorithm zero with the highest in. That's that vertex, and then
Uh, Okay, wait, I think I missed something at the end.
I added the this one to that. So you get all the one, two, three. Well,
Yeah, I can see that. Another option that I see is to like we add all the if we say we go with the highest in degree, I don't know, maybe put all of the ones with the um put all these guys at the back and then start with the highest one and trace our way back. So so go through all the vertices without degree 0, put them all in the back of the line, find the vertex in there with the highest degree, and then I would maybe say and then start with that vertex. Or we already kind of did that. And then trace back. Any issues that you could see? Not really that I know of either. There probably is somewhere. I want to, so what's the kind of, what algorithm or strategy are we working with here? What is the algorithm adapt that we've talked about? So we started with C and we went all the way, we traced it back to D. Instead of going A and then D, right? So there's a word that I'm looking for and 3 letters that I'm looking for what we just did. Yeah. DFS. Yeah, we just did traversal. Right? And that choice came from when we went to A and then we continued on to E and D instead of going A, and then D, right? We did depth first search. So this was DFS traversal. I will note that I have had this problem is basically asking you to reinvent an algorithm that is already known. So we were doing DFS, and there's the coming up with this process is coming up with a certain type of sort on a a kind of graph. So first of all, what kind of graph is this? Yeah. Yeah. So do you have an yeah, so no cycles tree. And another word for tree is acyclic, meaning A meaning no, cyclic meaning cycles. So there's no cycles. It's also directed, right? Because we have one edge points to another edge. And so this is what we call a directed acyclic graph. You'll see it abbreviated pretty much everywhere as a DAG, directed acyclic graph. That's what it stands for. And something we can find on a directed acyclic graph is something called topological sort. And so this question, in fact, has asked you to come up with how do we find a topological sorting? Let me pull something up. Maybe it helps if I spell topological correctly. Topological sorting. Okay. So this is the situation where if we have this sort of graph, this is a directed acyclic graph. We want to figure out an ordering where, let's see if we've got a picture. This is a special kind of topological ordering. So like you do this, so this example is like getting ready for school. So you get dressed first and then you go to school. So like then do each of these things in order. That's a topological ordering where the edges are going left to right. And that's kind of what we're doing here. Where except maybe the opposite. Maybe we want all the edges to go right to left so that the students don't throw things at each other, right? So the question has been to, let's see if we can find a better picture. Yeah. So we've been trying to do the opposite of this, right? This is our schoolyard and our line where we want this to be where the teacher is. And this is the backfill. Yeah. So yeah, so the idea of that the haters are more near to the front of the line and the Hades are at the back. So this question asks you to reinvent topological sorting. So so your homework, go home and read about topological sorting. Go through the kind of tutorials that are online. There's also a part in the textbook that asks about it. So now we can assume if you look at those, then we can assume that you know like what topological sorting is. And so that way on the test, if you get asked this question, you can say, do a topological sort on the graph of children so that the, I don't know, if we say bullies, so the bullies are at the front, the Hades are at the back. And so since this might require, since like this is the way that we order it, so the edges go from left to right, maybe we say flip the edges so that if Susie hates Jim, then there's an edge from Jim to Susie. So if this was on a test, you would need to say, here's what the edges are. So Susie hates Jim means the edge goes Susie to Jim or Jim to Susie. That's a choice that you make. But now that we know what topological sorting is, then it decreases the size of our answer from this is how we do it to I know what topological sorting is. Let's do that. Does that make it clearer? Cool. So your homework is to go and read about that and compare it. So compare it to the method that we came up with. See what the difference is. How is it different? Is there anything wrong with what we did? Go and look that up. This document will be uploaded to Canvas maybe 5:30 or so. Let me show you where it'll live. Down here, it'll be right here in the graph algorithms in class 2. So that's where this will live. So pull it up, look at what we wrote, compare it with topological sorting, and see what's different, which is better. Is there anything we were missing? Questions on that? Okay. Let's look at prerequisites. Okay, so we're in a particular academic program, maybe the computer science department, and we have a certain amount of required courses. So as you're, if you're not a graduating senior, you're probably getting ready for advising and figuring out what classes you're taking next semester. So you know that some classes have prerequisites. So I think the prereq for this one, so 374, the prereq is 222. And so you have to take 222 before you can get into this class. And you have to take 121 before you can get into 222. So we can draw the graph like this. So an edge between course X and Y means you have to take X before you take Y. So let's say we're given a list of all of these pairs. And how do we figure out that it's possible for someone to complete the program? Any clarifying questions before we break out? Yeah. I think, yeah, that's a good question. I think what I would interpret is that there is a pathway. Maybe you can also set, so there is a pathway. Maybe you could also say that like, how many semesters? 2, 4, 6, 8. Maybe you could also assume that there's 8 semesters. But I don't know, maybe it's a very long, maybe it's like a grad program where it's more than 4 years. Other clarifying questions? Okay, go for it. Okay, let's come back and briefly check in. So this one is a sample program from, what was it, University of Montana, where they've got Calc 1 and 2 that are the prerequisites for all this other stuff. And so the property, in terms of like, so I've decided that we don't care about the timeline. So we don't care about how many semesters we have. We just want to know that our map like this is valid. And so what's the property that makes this valid? Or what makes it invalid? What makes it impossible? Yeah. Yeah. So like if there was a situation where we needed Calc 3 to take Calc 1, then clearly we've gotten ourselves into like an impossible situation where we can't take Calc 1 to take Calc 2 to take Calc 3, but we need Calc 3 to take Calc 1. So the property is it needs to be acyclic, right? So now the question is, how do we figure out that it's acyclic? So how do we find that it's acyclic? This is what I'd like you to talk about. So we're given the pairs, and so obviously we know that, so maybe it's obvious if we have like, if we have Calc 1 and Calc 2, and we have something like this, then it may be obvious where we've got two pairs that are adjacent to each other. But what if it's more broad, like Calc 3 goes to Calc 1, or maybe advanced Calc 1 is a prerequisite for Calc 1. Maybe if that cycle is bigger, how do we find that cycle exists? All right, we've got maybe 13 minutes left till the end of class, so work on this. All right. So how do we do this? How do we figure this out? How do we tell if there's a cycle? Any ideas? Yeah.
If every vertex has a prereq, then their sense cycles.
If every vertex has a prerequisite, then there's a cycle. Yes. But what if that's not? So that is the answer, but how do we figure out that that's the case in our graph? How do we figure out that every vertex has a prerequisite? I know some people got the answer. Okay, so the question is, how do we find the presence of a cycle in this supposedly directed acyclic graph? We hope it's acyclic. Yeah.
Really, last says they do the test research. Is it a class more times than the total amount of classes? Then we know the possibility to
Okay, tell me the condition again. Yeah, so maybe more of like topological ordering. Yeah, that's, oh, no. Okay. Yeah, yeah.
We said we start with courses that don't have a prerequisite. We start with one course that doesn't have a prerequisite. Then we go through that activity path and it is let the node applies to know it's a cycle. And then when you're done with that, you go to the next report, if it doesn't have a prerequisite, and then you go through again, do the same thing,
Mhm.
and then there's no, you don't, anything.
Yeah, so the answer here is the easiest one is to use DFS in some way. If we look at information of depth first search, so we get different kinds of edges as we go through. So forward edges, which help us go through the graph as we visit nodes. Back edges, which points backwards from one node to one of its ancestors. Cross edges, which maybe we jump from one to the other. And so the answer here ends up being back edges. So as we go through DFS, it gives us this information. If we find a back edge, then there's a cycle. And that's the answer. So, we do DFS, and so we want to find if there is a cycle, because that means it's invalid. So as we go through DFS, if there is a back edge, then the program invalid. If no back edge is found, it's valid, right? So we think about it for a bit in class and say, how do I find this with like maybe this particular graph? And then we want to be able to say it in general. And the way we do that is we take an algorithm that we know how to run, and we see if we can tweak how it works or tweak the information it gives us to say this succinct answer. Where if we know what a back edge is and we know how DFS works, then here, if we've got a back edge, then that means there's a cycle. Okay, so go home, look over this. Your homework is to look at topological sort. Your homework is also to finish the video and work on the project. Have a happy Easter break, and I will see you on Tuesday.